I'm here to present my thesis project, essentially, that I have quite recently started. I'm in my second year of my PhD. Pontus Jonsson is my main supervisor, and Professor Rolf Stadler is my co-supervisor. And we are also collaborating with FOE, mainly with Theodor Sommerstad. We'll get into exactly what that is. But the title of the project is Sentience, and it has the subtitle Simulation-Based Reinforcement Learning Security Operations Center. And that is sort of the one-word summary of the project. So here's some more commercialization of me, former civil engineer student at Uppsala University. But I started with the project in 2021. It is funded by the Swedish Civil Contingency Agency, MSB, and it's also part of the CDIS initiative at KTH, which collects several projects that are related to cybersecurity and also the various Swedish defense agencies, mine being MSB. So the goal of the project is to develop the semi-autonomous security operations center in the long term. And what we mean by that is that we want to use autonomous agents to filter and analyze threat situations in our systems, our computer networks. And these should then produce policies that we can use to plan ahead or suggest suitable actions for the network operators that they can execute. But it's important to note that we're saying this is a semi-autonomous system, with emphasis on the semi. That we're not at a stage with AI and machine learning where we can just put all the keys to the car in the hands of the AI, that we want this to be something that can be a tool in the decision process, in the human decision process. And that this should be a resource and not a replacement to humans. So the current approach of this security operations center is that we are focusing on intrusion response for now. And we want to develop autonomous agents that can learn from data. Namely, we're using reinforcement learning from this. The problem with reinforcement learning is that it requires a lot of data, and with cybersecurity, it's quite difficult to get this data. So what we're doing is that we want to train these policies, these agents in simulation, and then evaluate them in real systems. So to formulate the simulation, then we formulate this as a defense exercise or cyber attack, depending on how we view it. We model it as a Markov decision process or a Markov game. So we build this on a modeling language that's called the meta attack language, where you can build these attack graphs that model parts of the cyber attack sequence. So each node in this graph would be one step of the full attack. And if you're wondering what all these arrows and nodes mean, we can go through it at the poster outside later. But the idea here is that you have an attacker agent that is traversing or executing actions from this attack graph, and then you have a defender agent that can then enable certain defensive measures in order to stop the attacker from performing whatever it is trying to do. Now, that is in the simulation, and that is kind of where we're at right now with the project. But of course, we want to do this in a real system. And in order to do that, we're taking help from or collaborating with colleagues from FOI to evaluate the system in their CyberRange crate. And they also have a tool to automate the attacker or the attacker agent that they call lore. So you we are able to automatically generate attack scenarios. And what we would want to do then is take our agents that we've trained in simulation and then be able to apply them in a real cyber exercise or cyber attack scenario that FOI can provide to us. But some preliminary results that I can show right now is one thing that we are interested in is since we have this attack graph that we need to somehow map to a real system, we are interested in knowing what happens if that process is not particularly good. What if you have a machine learning model that is supposed to do this, but it's not, it will produce a certain amount of errors. So we ran a whole bunch of experiments where you essentially have different levels of error in your observation space. So and then you can see the performance of the policies as that in that situation. And this was one of the baselines that we had, where all you're doing is as soon as you get your signal that an attack has happened, you immediately enable your defensive measure. And that works fairly well in terms of like keeping the attacker out, unless you stop receiving your signals, because then you have your attack or your defense will never trigger, and therefore the attacker agent will just slip past, which is why there's a big spike when the false negative rate gets too high. But in comparison, the one policy we taught with reinforcement learning takes a more conservative approach. It shuts down earlier, and therefore it's more resistant to when there's a high false negative rate, i.e. that you are losing alerts. So that's some promising early results, but we are hoping now to be able to evaluate this in a real system. So if you have more questions, you can talk to me at my poster outside in the exhibition hall, and that's everything from me.
Thank you.